Greetings, my friends. Today I'm here to talk about Mars colonization. The colonization of Mars has received interest from public space agencies and private corporations and has gained a large popularity in science fiction writing, film, and art. Organizations have proposed plans for human mission to Mars, the first step towards any colonization effort. But no person has set foot on the planet. However, landers and rovers have successfully explored the planetary surface and delivered info about conditions on the ground. Virtual visits to Mars using haptic technologies have been proposed and may precede humans visiting the planet. So, for the people out there who don't know the meaning of colonization, it's basically a process of establishing foreign control over target territories or people for the purpose of cultivation, often through establishing colonies or possibly by settling them. Okay, so why should we colonize Mars in the first place? Reasons for colonizing Mars include curiosity, the potential for humans to provide more in-depth observational research than unmanned rovers, economic interest in its resources, and the possibility that the settlement of other planets could decrease the likelihood of human extinction. Come on, being a multiplanetary species is a great achievement for humankind. So now that we know the reason to colonize Mars, what are the risks and challenges involved in the mission? Human space exploration is dangerous at all levels. After more than 50 years of humans traveling from Earth to space, the risk of spaceflight is similar to that of climbing Mount Everest. Mars is an unforgiving environment where a small mistake or accident can result in a large failure, injury, and death. Every component must work perfectly. Every system and its backup must function without fail, or human life is at risk. Difficulties and hazards include radiation exposure during a trip to Mars and on its surface, toxic soil, low gravity, the isolation that accompanies Mars' distance from Earth, a lack of water, and cold temperatures are other significant difficulties and hazards. There are three significant reasons which make Mars inhabitable: thin atmosphere, low pressure, and low temperature. Thin atmosphere. One of the most important attributes a planet needs to support human life is an atmosphere. Unfortunately, a very thin one clings to Mars and it's made up of all the wrong gases. According to NASA, our neighbor's atmosphere is mostly composed of carbon dioxide, has barely any oxygen, which humans need to breathe, contains very little nitrogen, which plants need to survive. Low pressure. On top of that, the atmospheric pressure on Mars is quite low, just 6.1 millibars compared to Earth's 1013.25 millibars. Pressure is critical to life on Earth. Without it, tiny pockets of air trapped inside a person's body would expand, eardrums would rupture, and water in the body would boil. Temperature. Mars is drastically colder than Earth, averaging minus 46 degrees Celsius with brutal lows of minus 143 in the winter and highs of 35 degrees Celsius in the summer on the equator. So how similar is the red planet to our Earth? Earth is similar to Venus in bulk composition, size, and surface gravity. But Mars similarities to Earth are more compelling when considering colonization. The Martian day is very close in duration to Earth's. A solar day on Mars is 24 hours, 39 minutes, and 35 seconds. Mars has a surface area that is 28% of Earth's, which is only slightly less than the amount of dry land that we have on Earth. Mars has an axial tilt of 25 degrees, similar to Earth's 23 degrees. As a result, Mars has seasons much like Earth, though on average they last nearly twice as long because the Martian year is about 1.88 Earth years. And one great discovery is that NASA's orbiters and rovers confirm the presence of water ice on Mars.
The Starship system is a fully reusable two-stage to orbit super heavy lift launch vehicle under the development by SpaceX. The system is composed of a booster stage named Super Heavy. Within the end of the decade, SpaceX will finally have a Starship capable of making the journey to Mars. The massive new spaceship has already reached suborbital capabilities. The massive beast has twice the power of Saturn V. It is a 160 feet tall, 120 ton heavy, most powerful human-built machine which will be able to carry 100 astronauts to Mars. It uses Super Heavy, the massive booster with 32 engines which fire up for 3 minutes, producing twice the power of Saturn V, boosting the Starship upper stage out of Earth's gravitational bounds. Super Heavy will then be dropped from the upper stage and it will head back to Earth to land and be reused again for the next Starship. The Starship in orbit will then perform a trans-Mars ejection which will set it on a course to reach Mars in 6 months. In these crucial 6 months, astronauts will have to live under high radiation risk that will significantly increase the possibility of developing cancer. They will sleep in bunkers present inside the Starship. Food is grown locally on the spacecraft. Lot of equipment is carried beforehand for their 2-year stay on Mars. Landing on Mars. Starship will enter Mars atmosphere at 7.5 km per second and decelerate aerodynamically. The vehicle's heat shield is designed to withstand multiple entries, but given that the vehicle is coming into Mars atmosphere so hot, we still expect to see some ablation of the heat shield. With the recent advances in commercial spaceflight comes a renewed public interest in colonizing Mars. However, there are significant changes in establishing a self-sufficient outpost on the Martian surface. A principal requirement is a reliable source of energy to keep the electronics and human occupants warm in the frigid Martian weather. To date, the two energy sources utilized for Mars missions have been sunlight and radioactive decay. A manned mission or a permanent settlement would likely also have to choose between these two. Though solar is increasingly popular on Earth, its intermittency, especially in the face of extreme weather events like long-lasting dust storms, makes it less attractive on Mars. Considerable storage would be necessary to provide adequate backup power, which would result in a very heavy system. In contrast, nuclear power could provide both steady electricity and a constant source of direct heat. Thus, from a reliability perspective, nuclear power appears better suited to powering a small Mars colony. However, this is not to say that nuclear power is necessarily the best technology for extraterrestrial planetary outposts. It does introduce a set of safety and environmental concerns that may necessitate further testing and research to address. Now, let's come to the most important part. Food production on Mars. When the astronauts land on Mars, there will be storable food from Earth waiting for them to use. The storable food from Earth will only serve as emergency rations, which means the astronauts will try to eat as much as fresh food that they produce on Mars as possible. It is likely that algae and insects will also be a part of the diet on Mars. Food production will occur indoor under artificial lighting. A thick layer of Martian soil on top of the inflatable habitat will protect the plants and the astronauts from radiation. CO2 for the plants is available from Mars atmosphere and water is available through recycling and the soil on Mars. Nutrients for the plants could come from recycling human waste or could be imported from Earth. Any plant production surplus will be stored as emergency rations for the second crew and for emergencies. Non-edible parts of the plants will be recycled or stored until more advanced recycling equipment is shipped from Earth. Water, the most important thing for humans. On Mars, water can be extracted from the soil. The rover will select the location for the settlement primarily based on water content in the soil. This is expected to be at a latitude of between 40 and 45 degrees north latitude. Water extraction will be performed by the life support units. The rover will deposit soil into a water extractor in the life support units. The water extractor will heat the soil until the water evaporates. The evaporated water will be condensed and stored. The dry soil will be expelled and the process will be repeated to extract more water. About 1500 liters of reserve water will be stored in each life support unit, which will be consumed primarily at night and during periods of protracted low power availability, for example during dust storms. Since Mars has gravity, water can be used in the same way as on Earth. Each astronaut will be able to use about 50 liters of water per day. The water will be recycled, which takes much less energy than extracting it from the Martian soil. Only water that cannot be recycled will be replaced by water extracted from the soil. Oxygen. Oxygen can be produced by splitting water into constituent parts, hydrogen and oxygen. An instrument called MOXIE will be able to produce oxygen using this method. The oxygen will be used to provide a breathable atmosphere in the living units, and a portion will be stored in reserve for conditions when there is less power available, for example at night and during dust storms. The second major component of the living unit's atmosphere, nitrogen, will be extracted directly from the Martian atmosphere by the life support unit. It's humankind's nature to explore our surroundings if it can be done. Do we deserve to become multiplanetary? Although Mars is an unforgiving environment where a small mistake or accident can result in a large failure, injury, and death, we must not fail to forget that 50 years ago we sent humans to the moon at a time where no advanced technology was invented or calculators. Humans were the calculators. Thus, this mission is just a matter of time and patience. I would like to end this video with a quote by Carl Sagan. Across the sea of space, the stars are the other suns.